In this video, we're going to talk about the three forces that affect wind. The first force would be the pressure gradient force. That would be the main force that drives wind production. The second effect upon the wind would be the Coriolis force, also known as the Coriolis effect. And then the third force that acts upon the wind is friction. And we're going to talk a little bit more about friction in another video since it only has an effect on wind at the surface. So starting with the pressure gradient force, it's really just a fancy way to say wind blows from high to low pressure, and it is the main cause of wind creation in our atmosphere. The reason is because the atmosphere always wants to be stable. And so when it is unstable, especially when we talk about air pressure, our atmosphere tries to compensate by blowing wind from high to low pressure. Or when we want to actually picture what a pressure gradient is on a weather map, we draw what is called isobars, and they're points on a weather map that connect the same points of pressure, and isobars are drawn aloft and at the surface. So at the surface, when we look at a surface map, we say that if the isobars are closer together, the pressure gradient is larger and therefore the wind is faster. So just looking at this diagram here, on the left hand side we have high pressure, on the right hand side we have low pressure. And so here when we look at these isobars here, and they're not drawn straight like this is just for visualization purposes. So here we have 1016 millibars. On the right hand side we have 992 millibars, so you can see where high pressure is, and you can see that the wind would be blowing from high to low pressure. Well, when the isobars are further apart from one another, we say that's a weak pressure gradient, and therefore the winds are weak because the differences in pressure per area aren't that great. So this is really just a 4 millibar difference. But now we go all the way to the right hand side, and here we see that we have 996 millibars versus 992 millibars, and yes, that's only a 4 millibar difference, but you see the space between these isobars are smaller. So that means that pressure, yes, even though it's changing only by 4 millibars in both examples, you see that the change is quite fast, and therefore that is a steep pressure gradient, and that means that winds are relatively stronger. So here on an actual weather map, you can see up in the left hand corner we have a nice big area of low pressure with a center low pressure of 968 millibars, which is quite low. So this is a quite of a big low pressure system, quite of a storm system out here, wherever this is. But as you go towards or you look towards the right hand or the bottom right hand part of your screen, you see here that the pressure gradient is much weaker, especially as you go almost off to the bottom right corner. So here the wind speeds are very light. They're only about 5 to 10 knots, even non-existent at all in some locations. But closer to the center of the low here, in the heaviest spiral bands, we have wind speeds of anywhere from 40 to 45, even we have some 50-knot winds down up and through here. So this is much faster, and you notice how the isobars are much closer together. Now, another great example of a pressure gradient in the real world is what is called a sea breeze. And so a sea breeze is really just a term for the wind blowing off the water onto the shore, but there's an actual pressure gradient difference in this scenario. So what happens is that during the day now, sea breezes are actually more common during the spring and summer months. And that's why normally when you head to a beach on a hot summer day, it's usually a lot cooler than it would be in inland locations. So remembering what we've learned about the heating differences between land and water, we know that the land heats up faster than the water heats up. So that means the air that's over the land is warmer than the air that's over the water. And so what happens is that you have an area of relatively low pressure over the land, and you have an area of relatively high pressure over the water. And so what happens is that you have this pressure gradient that results from the air being cooler and being more dense, and therefore the air over the water is cooler and features higher pressure. So that means that the cooler wind cools locations along the coastline. Here over the land, The air is warm, more dense, and eager to rise. So that's why we have an area of relatively low pressure. And at night, and especially in tropical locations, the land and sea breeze days are more common than in the United States, especially if you don't live on a coastline. But here on a land breeze night, it's really just the opposite effect. So again, knowing the thermal properties of land versus water, we know that with the land that cools off relatively quickly at night, the water stays relatively warm. So now you just have the opposite effect. So now cooler, more dense air, which creates an area of relatively higher pressure, sits at the surface on the land, and that the water is still relatively warm. That means the air is still relatively warm over the water, which means that air is less dense and is still eager to rise. So that creates an area of relatively lower pressure. So here, high pressure will blow towards low pressure. And so that's just an example of what pressure gradients look like in the real world.